Welcome back. We're still focusing our attention on more stoichiometric problems and try to understand some of the important things that we have to take note in as far as sharpening our skills of responding to stoichiometric problem. And it's also very important to note that the questions on stoichiometry can be asked on any topic as long as it involves a chemical reaction. Now let's look at one more example in terms of these questions on stoichiometry. Right. Okay. Now we have got 40 grams of iron metal and 35 grams of chlorine. Okay. These are the quantities in terms of mass that are given. These two, they react to form iron 3 chloride. Very, very important in terms of chemical formula. Iron 3, because iron is a transition metal, it simply says to us that in this ionic compound, iron has an oxidation number of 3+. Okay. Right, but the balanced equation of reaction is already given to us. It says 4 moles of iron reacts with 3 moles of chlorine, right, to give us 2 moles of iron 3 chloride, right? So what does this tell us? It tells us that the stoichiometric ratio in which these substances participate in this chemical change is 4:3:2, right? Now the first question, define, that's the action verb, right? So in as far as definitions are concerned, we need to be very, very specific and pay attention to the key words. So our examination guidelines are our point of reference in as far as remembering definitions. We must capture the key words in the correct context. And also remember that in as far as definitions, because it's just about remembering. So it's either you get the full 2 marks or nothing. So you need to practice our definition always. These are our quick wins. These are our easy marks in as far as questions are concerned, right? So the definition of the term limiting reagent. Okay, what is a limiting reagent? This is the substance, okay, the reactant, okay, whose quantity, okay, or whose amount, okay, determines the amount of product obtained. Of product in a reaction, okay? So in other words, we are saying that this is the substance or the reactant that gets used up. So the amount of product that is obtained in a chemical reaction depends on the quantity of the limiting reagent, okay? Now the follow-up question says, calculate which of the reactants will be used up in the reaction, right? Okay, so the one that is going to be used up, in other words, we would rephrase the question and say, what is it that the question demands of us? It actually wants us to identify by means of calculations, that is, the substance that is a limiting reagent, okay? Right, so this is a stoichiometric calculation. What are we given? We are given masses, right? But then what is the SI unit of quantity of matter in a chemical reaction? We talk about the mole. Now, let's check, because we've got the stoichiometric ratio of 4:3:2, okay? Now, we are paying our attention on the reactants because we want the limiting reagent. So we can safely classify this question under limiting reagent, okay? So it's all about the limiting reagent, okay? So we're going to do a couple of calculations for us to arrive at that. So the stoichiometric ratio is there from the balanced equation. Now the next thing that we ask ourselves is how many moles are there for each of the sample of substance of the reactants, right? So we know that the number of moles, the moles of iron rather, okay, is equals to mass of sample over molar mass, right? What's the mass of iron sample that is given? It's 40 grams, right? Divided by the molar mass, which is 56, right? So let's calculate the moles of iron in this case. So the moles is going to be 40 grams divided by 56 grams per mole. That gives us, as a decimal fraction, 0.71 moles, okay? So this is equals to 0.71 mole, okay? What about the moles of chlorine that we have. So the moles present for chlorine, which is a diatomic, molecule, is equals to mass of the sample over the molar mass. Okay, the given mass of the sample is 35 grams, right? Divided by the molar mass, which is 2 multiplied by 35.5, right? So if we go to our calculator, what do we get? We'll have 35, okay, divided by 2 multiplied by 35.5, okay? Right, close that bracket. Okay, this gives us a value of 0.49 moles, right? So there's 0.49 moles of chlorine, right? Now, let's ask ourselves an important question. Let's say, for argument's sake, we know that for every 4 moles of iron, there should be 3 moles of chlorine, right? So if we say, for argument's sake, if let's say all the iron has to react, the ratio of iron to chlorine gas is actually 4:3, right? So 4:3. Now let's say assume that the entire 0.71 moles reacts. How much of chlorine do we need? Let's say that is X, all right? So by simple calculation, the X in this case becomes 3 multiplied by 0.71 by cross multiplication over 4, right? All right, then we can evaluate that and try and decide if indeed all the iron will react. And when we say all the iron reacts, we are saying, in other words, iron we are just checking by trial and error, is iron our limiting reagent or not? Okay, so what do we have there from the calculator? We get 3 multiplied by 0.71, right, divided by 4. Okay, what does that give us? It gives us 0.5, right? Now, in other words, for all the iron to react, we need 0.53. But how much of chlorine do we have? We've got 0.49. Then it means all the iron will not react because we can't have 0.53 of 0.49 reacting. In other words, we have less of chlorine. Now let's do it the other way around and use the same ratio of 4:3, all right? Let's say all the chlorine reacts. Okay, how much of chlorine do we have? 0.49, right? And then how much for 0.49, how much of iron do we need, right? So it's still the same ratio, iron is to chlorine, okay? Right, so by simple calculation, our X becomes, we cross multiply 4 multiplied by 0.49, right, over 3, okay? So if we can check that on our calculator, what do we have? We have got 4 multiplied by 0.49 divided by 3, okay? Right, our answer is as a decimal fraction is 0.65. Now, what are we saying? We are saying X, okay, if you can go back to that, okay, we are saying X is equals to 0.65 mole, right? Now, what are we saying? We are saying that if all the 0.49 of chlorine reacts, how much of iron is needed? It's 0.65. Already, how much of iron did we have? We've got 0.71. It means all the chlorine will react, and some of this 0.71 moles will actually react, and some of it will be left. So, in other words, we are saying that chlorine is our limiting reagent. So, therefore, we are saying chlorine gas is the limiting reagent, right? If chlorine is the limiting reagent, what does it say by implication? We are saying that iron is the one that is in excess because of the 0.71, only 0.65 moles of iron will react based on the stoichiometric ratio, right? Okay. Then the follow-up question says, how many grams of the other reactants are in excess? Very important question, right? We had, because iron, okay, is in excess. Okay, not all the iron actually reacts. Okay, so the remain unreacted moles, okay, of iron, okay, of iron is equals to actually what we started with, 0.71 less 0.65. If you can quickly go back and confirm, because what actually reacts is 0.65, right? So 0.65 moles. So how many moles are there? We can quickly verify that and say, okay, we started with 0.71. Of that 0.71, only 0.65 of it reacted, okay? We need to subtract that, 0.65. So how much is unreacted as a decimal fraction? 0.06, right? So only 0.06 moles are unreacted. But the question says, how many grams? So the moment it says grams, we're interested in which quantity? The mass unreacted, okay? So mass that is unreacted will change these moles back to the mass. So we know that moles of substance is mass over molar mass. But here, what are we talking about? We're talking about iron because it is in excess, right? Now, the moles is 0.606 that is unreacted, okay, is equals to whatever mass we're looking for over 56. So the unreacted mass is actually that product, right? So we have 0.06 multiplied by the molar mass of iron, which is 56. This gives us, as a decimal fraction, 3.36 grams, right? So 3.36 grams of iron is unreacted, okay? So that's the main idea in as far as the stoichiometric calculation. So if we say from the ratio of 4:3, right, and then all of the chlorine reacts, it means chlorine is the limiting reagent, which will determine the amount of iron 3 chloride that will be formed. So if chlorine is the limiting reagent, it tells us that iron is the one that is in excess. So in terms of language, let's pay attention to that. We understand that a limiting reagent gets used up, okay? And once that limiting reagent has been used up, what essentially happens, the reaction stops. And then we would say that the reaction has reached completion. Okay, and then for the other substance that is not a limiting reagent, we'll describe it in terms of the substance being in excess. Then we always work in moles because that's the SI unit of quantity of matter. So we can change the unreacted moles to actually determine the mass that remains in terms of the excess substance. Okay, right. So these are some of the ideas that are very important, right? Okay, now the last follow-up question says, how many iron 3 ions are present in the product, right? So in terms of the moles, we know that 4 of iron forms 2 moles of the iron 3 chloride, okay? And then 3 of chlorine actually form 2. Okay, it's a very interesting question because we're talking about the number of ions. So this has got to do with the Avogadro number of substances, okay, of particles of a substance based on the mole concept. So how much of iron 2 is formed? Iron 3 chloride is formed. That's the question that we want to ask ourselves. How many moles will be formed, okay? So 4 of iron forms 2. So the ratio of iron to iron 3 chloride, okay, which is Fe2Cl3, is the ratio is 4 produces 2, right? So how many moles of iron did react? We said 0.65, okay, moles. So 0.65 will form half that because 4 forms 2. 0.65 will form half that. So if we go to our calculator once again, we'll say 0.65 divided by 2, okay? This gives us, as a decimal fraction, 0.325, okay? So this will be 0.325 moles, okay? Right, but then if we go back to this equation in terms of per formula unit, what do we have? We have got Fe okay, 2Cl3, right? So in terms of ions, it will be 2Fe, okay, 3 plus, right, and plus 3Cl minus. So for every mole of iron 3 chloride, there is double the number of moles of iron. So if we have got 0,325, okay, moles, it will form 2 times that, which is 0,325, okay? Right, so this is the actual number of ions of Fe3 plus, okay? But then we know that number of moles is equals to a number of particles divided by the Avogadro number, right? So we've got this, which is 2 multiplied by 0,325, right? Is equals to number of, which is the Fe3, the number of particles, then divided by 6,02 times 10 exponent 23, which is the Avogadro number, right? So the number of particles is actually a product of that, okay? So if that's the case, we'll go to our calculator, okay? What does it give us? It's actually a product. We can isolate the number of particles, okay? So which means it's 2 multiplied by 0,325, okay? Times Avogadro number, which is 6,02 times, okay, times 10 exponent 23, okay, right. Then this gives us the number. So how many particles are there? So that number is actually 3,9 times 10 exponent 23, okay. 3,91 times 10 exponent times 10 exponent 23. So this is the actual number of particles, okay. So, you know, the mole concept is quite broad, and the questions on stoichiometry can be on any topic. So it is about the mole, okay. So for now, we'll just want to try and say, okay, these are the main things, you know, in terms of the mole concept, but there is more. A lot of practice will actually boost our confidence in as far as this is concerned, right? We'll take a short break for now, and then after that, we'll continue with more revision on problems based on stoichiometry. Let's take a short breather for now.